Hi, folks. So this is your lecture for Monday of week 2. The game plan for this is that I'm gonna work through the problems from week 1's Thursday activity. I'm gonna do 1, 2, 4, and 5, not 3, just because I want to try and get through um a bunch of these, and I don't want this lecture to be too long. But if you would like me to work out question 3, just ask. Okay, so starting with question 1, I'll read it. An Olympic class sprinter starts a race with an acceleration of 4.5 meters per second squared. What is her speed 2.4 seconds later? And then sketch a graph of her position versus time for this period. So we will start out with our knowns and unknowns. Knowns. So let's see. Acceleration of 4.50 meters per second squared. The time interval they gave us is 2.40 seconds. Since people start races not moving, yeah, we can say our initial velocity is 0. We also get to decide her initial position. So we'll say that's 0, 2. And let's look at our unknowns. So we don't know what her velocity is at this 2.4 seconds. I'm going to call that V final. And we don't know what her displacement is either at that point. I think that's all we want to worry about right now. So next thing we can do is draw the picture. I'm not going to try and draw it looking like she's running. I tried that for the solutions to the assignment. And it just did not look like that at all. So we're just gonna use our imagination. So initially 0 meters per second. And then sometime later at this time interval of 2.40 seconds, we are at velocity final. So she's moving with some sort of velocity. Okay, so drew the situation. Next up is our equations. So let's just write them all out. We have V final equals V initial plus A times the time interval. And we have X final equals X initial plus the initial velocity times the time interval plus 1/2 the acceleration times the time interval squared. And then finally, V final squared equals V initial squared plus 2 times the acceleration times the displacement. So I'm leaving out the equation for no acceleration, like with constant velocity, because we know we have acceleration. So let's go through these and see what we know, what we don't know. We don't know final velocity. We know initial acceleration and time interval, so that's a good start. We don't know the final position. We know initial velocity, time interval, acceleration, and time interval. Okay, but they didn't ask us for the position right now anyway, for part A. And finally, final velocity squared, yep. Initial, yes to acceleration, no to displacement. So since the first part A, asked for the velocity after 2.4 seconds, we should use that equation. So I will put that this is part A, and we are using V final equals V initial plus A delta T, or acceleration times the time interval. And our initial velocity is 0, so look at that. We get to cancel that out. So our equation's even easier. V final equals acceleration times the time interval. Now we can just plug those in. So acceleration is the 4.50 meters per second squared, and the time interval is 2.40 seconds. And this is 10.8 meters per second for the velocity after 2.4 seconds. And we can see that the seconds in the time cancel out one of the seconds in the denominator of the acceleration, giving us just meters per second left. Okay, maybe I'll highlight. That's the answer. Okay, but then B, it asks us to plot the position versus time. So in order to do this, we need to know those data points. We need the position at different times. And we can find that, like calculate it ourselves. So we have this other equation that we only had one thing we didn't know, which was the final position. So we can just use that and calculate that position at different times. So before we worry too much about like which time intervals and things, let's just look at our equation first. So x final equals x initial plus initial velocity times the time interval plus 1/2 the acceleration times the time interval squared. So initial position, we said that was 0. Initial velocity is also 0. So we're left with a simpler equation. The final position is 1/2 a times the time interval squared. Okay, so we'll use that to calculate. And then this part, because it's not really specific in this question, you can kind of decide the intervals of time that you want to use. If you want to say like, I'm going to measure at 1 second and 2 seconds, for example. I'm going to go by 0.4 seconds, which seems weird, but it's because we're going to 2.4 seconds. So that way I can like end on 2.4 seconds. But again, you get to decide that part of things. So unless like the problem actually specifies, which this one doesn't. So we're going to have position in meters and time in seconds. And I'm just going to list our little time chunks. So initially we're at 0. Then we're at 0.4, 0.8, 1.2, 1.6, 2.0, and finally 2.4. So again, that's just counting by 0.4 seconds. And now we just calculate with those different time intervals. So we know that the initial position is just 0. Oops. So that one's easy. And then we can just plug stuff into the equation. So it'll be 1/2 the acceleration, which is about 4.50 meters per second squared, times whichever time interval we're at. So we'll start with 0.4 seconds. So that one's 0.4 seconds squared. So this one gives us 0.456 meters. And it looks like we went in with only one sig fig here. So it looks like we should round this to 0.5 meters. So that's our first position. Well, second, I guess. Our first is 0. Okay, let's keep going. So this part gets a little repetitive. We're just going to continue this calculation for each of them. Let's see, 0.8 is next. This one gives us 1.44 meters. And actually, let me think about this. I don't want to just round it to 1 sig fig, I don't think. So we're going to break the mold a little bit, and we're just going to keep it at 2. So we'll say 1.4 meters. And maybe we'll keep this one at 2 also, so 1.46 meters. I know that's not perfect sig fig etiquette, but oops, we don't need to put meters there. I already put it at the top. But we also don't want to lose information by rounding too much. Okay, let's see. 1/2, 4.50 meters per second squared times 1.2 squared. This one is 3.24 meters, or we'll say 3.2 meters. 3.2. Okay, 3 more. Gotta make them fit. Final equals 4.50 meters per second squared times 1.6 seconds squared. This one is 5.76. meters or 5.8 meters. That's what we'll put here, 5.8. And then 2 more left. So x final equals 1/2, 4.50 meters per second squared times 2.0 seconds squared. This one is, wait a second. Oh, I see. 9 meters. And then finally, 1/2, 4.50 meters per second squared times 2.4 seconds squared. And this one is 12.96 meters. I think we have to just round this one to 13 meters. Okay, so that's our data, and now we're gonna plot it. I'm gonna do that on the next slide. Or next page, I guess it's not really a slide. Maybe I'll copy this over though, just so we have it. Copy. Okay, because I already drew what the graph will look like, but this is something you can also figure out once you've calculated all your data. You can say, okay, I'm going from this time to this time, and from this distance to this distance, I should distribute these in some way. Okay. Let's start. We start at 0, and then at 0.4 seconds, we're at 0.46 meters. So that's a little bit less than halfway to the 2. So, I mean, we'll do our best there. At 0.8, we are at 1.4. So that's kind of halfway between our last point and the 2. Pretty close. And then we're at 1.2 and 3.2. So that is going to be just above halfway between 2 and 4. So like right there. 1.6 is at 5.8. So now we're pretty close to 6. And then at 2, we're at 9. So that's halfway between 8 and 10. And finally, at 2.4, we're at 13, which is halfway between 14 and 12. 12 and 14. Okay, and then this is kind of, it should be anyway, a parabola shape. Because we know we have acceleration, which means that the velocity is changing. So we don't expect our position graph to be linear. It shouldn't be a straight line if the velocity is changing with time, which it is. Okay, problem 1, good job. So now problem 2 will be shorter because we don't have to make a plot. Okay, so for this one, we have a bicyclist begins accelerating from rest at 1.2 meters per second squared, and we want to know how long it takes them to get to a speed of 6 meters per second. So let's go knowns. Rest, so the initial 0 meters per second. Acceleration is 1.2 meters per second squared. Final velocity we're looking at is 6 meters per second. And then we're also going to say our initial position is 0 meters, just in case. Unknowns, we don't know how long that takes, and we don't know the total displacement. Cool. And then we can draw it. I will try to draw a bicycle. I feel like I did okay. Don't correct me on that. When drawing the solutions, but okay, well, this is no longer the same size. That's fine. Okay, so this is our initial velocity is 0. And this is when we're at velocity final equals 6 meters per second. And this is a time interval later and a displacement later. And through that time, we're accelerating with our acceleration we have. Cool. Okay, now our equation. So v final equals v initial plus the acceleration times the time interval. X final equals x initial plus v initial times the time interval plus 1/2 acceleration times the time interval squared. And finally, v final squared equals v initial squared plus 2 acceleration times the displacement. So let's go through these. Let's see, we have v final, v initial, acceleration, and we don't have the time interval, but we want it. We don't know the final position. We know the initial. We don't know the time interval. We know acceleration. We don't know the time interval. We know final, initial, acceleration, but we don't know the displacement. So it's only asking us for the time interval, saying how long. So we'll just use this one because the only thing we don't know in that equation is the thing they want us to find. So V final equals V initial plus acceleration times the time interval, and start off with this is 0. Yeah, and that puts us at V final equals acceleration times the time interval. And then we can just divide acceleration on both sides because we're solving for the time interval. So let's see, final velocity divided by acceleration equals the time interval. So 6 meters per second divided by 1.2 meters per second squared is going to give us time interval of 5 seconds. Look at that, 2 down, 2 to go. Okay, so again, we're skipping question 3 because, again, to save on time, but also because it was a little bit longer and a little bit repetitive. So, oops, how did this? 1 second. Okay, now for question 4. At the end of a race, a runner decelerates or accelerates, but negative, slows down from a velocity of 9 meters per second at a rate of 2 meters per second squared. How far does she travel in the next 5 seconds? What is her final velocity? And then we want to evaluate that result and say, does it make sense? So, knowns and unknowns. Let's pick a color. Please green. Okay, what do we know? We know the initial velocity is 9.00 meters per second. We know acceleration is 2.00 meters per second squared. We can say our initial position is 0. Oh, and we are given a time interval of 5.00 seconds. Unknowns, the final velocity and the displacement, although we're not asked for the displacement. So I'm gonna just draw this real quick. We have our runner. Maybe she passes the finish thing. Hooray. And she's slowing down. So initially she has this velocity, and she has some other velocity or 0, we'll see. And then this whole time in between, she was accelerating but slowing down. So negative acceleration. Okay. Now, let's do our equations. So final velocity equals initial velocity plus acceleration times the time interval. Final position equals initial position plus initial velocity times the time interval plus 1/2 acceleration time interval squared, and V final squared equals V initial squared plus 2 acceleration. Okay, so let's look through these. We want the final velocity, so that one, we don't have it yet. We know the initial, we know the acceleration and the time interval, so we'll probably use this equation. Oh, but actually, we don't want, oops, that's for part B. Skipping steps. We want to find how far she travels in the next 5 seconds, and then we want to find the final velocity. So we want this final position. We know initial velocity, time interval, acceleration, and time interval full. And then this one, we don't know the final velocity. We know initial acceleration, we don't know time interval. So we're not going to use that one. We're going to use this one for part A. So x final equals x initial plus initial velocity times time interval plus 1/2 acceleration times time interval squared. And then we're going to say our initial position is 0. So, and then we can just plug in everything else. Initial velocity is 9.00 meters per second. Time is 5.00 seconds plus 1/2. Acceleration, remember, it's negative because it's decelerating, slowing down in the opposite direction of the velocity. Meters per second squared times 5 seconds squared. So this one, I did this calculation earlier, gives us a position of 20 meters. So that's how far she traveled in those 5 seconds. And then we want to look at the final velocity. So we'll use that equation that we have up above. V final equals V initial plus the acceleration times the time interval. And we can just plug this stuff in. So V initial is 9.00 meters per second plus, so negative acceleration still 2.00, negative 2.00 meters per second squared times 5.00 seconds. So this gives us, oddly enough, a final velocity of negative 1 meter per second. So interesting. But the next part of the question asks us if that makes sense. So yeah, let's think about that. Does it make sense? Not really. No. If she was moving, let's look at that. Let's draw it really quick. So initially, she's moving at 9 meters per second. And then we're supposed to see like negative 1 meter per second. So she's going backwards. She turned around. It's not really how races work. So no, this doesn't make sense. And part of the reason why is that she doesn't need to decelerate for 5 seconds. And let's look at what I mean there. So if we look at the same equation as part B, so V final equals V initial plus acceleration delta t, but instead we say, what time will it take so that the final velocity is 0? So we can solve for final velocity. Yeah, we'll do that. V final, I'm sorry, solve for the time interval. It's already solved for final velocity. Okay, so that's going to be subtracting the initial velocity from both sides, giving us V final minus V initial equals acceleration times the time interval. And then we're going to divide acceleration on both sides. That gives us V final minus V initial over the acceleration equals the time interval. And the final velocity here we said is 0. 0. So minus initial velocity is 9.00 meters per second divided by our acceleration of negative 2.00 meters per second squared. So those negatives are going to cancel. And what we end up with here is a time interval of 4.5 seconds is what's needed to go to a velocity of 0. So that's why what we found in B doesn't make sense, because it doesn't take her 5 seconds to get to a stop. It only takes her 4.5 seconds. Okay, last example now. I already have my picture because I feel like I drew a pretty good car, and I'm not going to be able to do it nicely again. So anyway, let's talk about the situation. I will describe the picture and then we'll do our notes and unknowns. So we have a car traveling at a speed of 30 meters per second, which is a typical highway speed on wet pavement. And the driver sees an obstacle ahead and decides to stop. From this instant, it takes him 0.75 seconds to begin applying the brake. That's what's called his reaction time. The time it takes his brain to realize, oh, I need to stop, and then his body to actually initiate that process. So, but once the brakes are applied, the car experiences an acceleration of -6 meters per second squared. And we want to know how far the car travels from the instant the driver notices the obstacle until it stops. Okay, so let's take a look at this with the picture I have here. So in orange, this initial one is just like at the beginning, that moment when the driver notices an obstacle. And then a little bit later, we have this yellow version of the car to indicate that it's like a little bit later in time. They're still moving at this initial velocity, but some time interval has passed. Oh, the 0.75 seconds has passed. And then he did travel some distance in that time, but that's when he starts the brake. Okay. And then we have the second part, which is going from the initial velocity to 0. And that is another time interval and another displacement. Okay. So let's do knowns and unknowns. No. So we have an initial velocity of 30 meters per second. We have an initial time interval, which I'm going to call time interval 1 of 0.75 seconds. We know we're trying to get to a final velocity of 0. We can say our initial position is 0, and then our acceleration is -6. I think 6.0, yeah, meters per second squared. Unknowns. So we don't know this first displacement here, but we know the time interval, so that'll help. And then we don't know the second displacement or the second time interval. And we also don't know what is the total displacement. And this total displacement, maybe I'll just write it here, is going to be the displacement initially plus the second displacement. So it's going to be from this position to that position. Oh yeah, and I did write this in the solutions for it. So distance before hitting the brake, braking, and distance while braking. Okay. So first we want to find that initial displacement from when his brain realizes he wants to stop to when he is able to, put his foot on the brake. So to find that, oh no, it's a displacement, not a position. Displacement 1. So maybe I'll write our equations over here. So what do we got? V final equals V initial plus acceleration times the time interval. X final equals X initial plus V initial delta T time interval plus 1/2 acceleration times the time interval squared. And finally, V final squared equals V initial squared plus 2 acceleration times the displacement. So one thing I want to do is for this specific chunk of time, let's just write down what our knowns are. So we have an initial velocity, 30 meters per second. We're not accelerating at this point. Meters per second squared. And we have a time interval of 0.75 seconds. And then we want to know what our displacement is, okay? So let's go through our equation looking at that, or these equations looking for those. So there's not a change in velocity happening. So it's not actually these guys. We can still use this one, I think, because, okay, we want the displacement, but we can use the final position as part of that since we decided the initial position is 0. So, okay, we have an initial velocity, we have a time interval. Technically, we have an acceleration, it's just 0. And time interval. Okay, it looks like we can use that equation. Let's simplify it though, because clearly some of that stuff we don't need. So x final equals x initial, the initial delta t plus 1/2 acceleration delta t squared. Okay, so acceleration is 0, so that goes away. And the initial position is 0, so that goes away. So this is just given by the initial velocity times the time interval. So 30 meters per second times 0.75 seconds. That gives us a distance of 22.5 meters for x final. And remember, keep this in a different color. Displacement is final minus initial. If our initial is 0, then displacement equals the final position. So this is also displacement 1. Okay, cool. We have that part. That's only kind of half of what we want. Oops. So now let's do the next part. There's some room to get started anyway. So to find the second displacement. Now, again, let's write knowns and unknowns specific to this. So again, the initial velocity is 30 meters per second. The final velocity for this one is going to be 0. Let's see, acceleration is negative 6.0 meters per second squared. Yeah, so that's knowns. Unknowns, that displacement that we want, and we don't know the time interval either. So let's go back up to these equations and see. Okay, we know final, initial, acceleration. We don't know the time interval. Let's see. We don't know the final position. Technically, we can know the initial. We'll give that one a check mark. We know that. We don't know the time interval. So actually, this equation is not going to be useful. We know the acceleration, but we don't know the time interval. This one, we know both velocities and acceleration, and we want the displacement. Okay, cool. This is the equation we want to use. So let's bring that down here. V final squared equals V initial squared plus 2a times the displacement. So now we're just going to solve this for the displacement. So we'll subtract V initial squared from both sides, giving us V final squared minus V initial squared equals 2a times the displacement. And then we'll also divide both sides, divide both sides by 2 times the acceleration. So that will give us V final squared minus V initial squared over 2 times the acceleration equals the displacement. And that's what we're looking for. And then one more thing we can do is say that V final is 0. So the actual equation here is going to be negative V initial squared over 2 times the acceleration. Okay, and then I guess there's enough room to do it down here. So displacement 2 is negative 30 meters per second, whole thing squared, divided by 2 times negative 6.0 meters per second squared. This is going to give us a displacement of 75 meters. And then there's just not quite enough room. But maybe I can make room actually. That is displacement 2. And we want the total, which sorry for putting this kind of in the middle of things, but I ran out of space. X total, remember, is just displacement 1 plus displacement 2. And displacement 1 is 22.5 meters. Displacement 2 is 75 meters. So this gives us a total displacement of 97.5 meters. So in the time it takes the driver to see that obstacle, realize he needs to stop, and then actually stop, He travels almost 100 meters. That's pretty far. So there is our answer. And that is the process for solving it. And you'll notice that, again, I had to break this one up into these different chunks and look at the knowns and unknowns kind of for each of those chunks of time. So yeah, that is all for this lecture. You have an assignment to work on after this. And I will see you on Tuesday.